authored paper. So these are the 4 co-authors: Bleckermann, Hauenstein, Autumn, and also Christian Ranestad. And the main work is sort of based on earlier work of Greg Bleckermann, so he is sort of the most important author here. And I like to start with 2 warm-up questions. And then as people come in, we'll get to the real talk in about 3-4 minutes. So the first, from high school we know that a quadratic polynomial in one variable is non-negative if and only if, well, the a and c are non-negative, but most important, the discriminant should be non-negative. So first question is, let's do the same thing for polynomials of degree 4. So we have 5 coefficients, a, b, c, d, e, and e. We look at values of those coefficients, where this is a non-negative polynomial. That's a convex cone, a 5-dimensional cone, and we're interested in the boundary. So what is the degree and defining polynomial of this boundary? And the second question is, how would you describe the dual cone? C dual to that cone, and I like to find a good inequality representation of this dual cone. Well, the first one, so the algebraic boundary of non-negative quartics, well, if you have a quartic that's strictly positive, right, it'll hit the boundary when the graph touches the x-axis. Then it's in the boundary. But at that point, there will be a double root, right? So a polynomial that is non-negative but just touches the x-axis in its graph has a double root. So there's necessarily a double root. That means the discriminant vanishes. Okay? So the answer is the discriminant, which is this polynomial of degree 6. So if you type my problem into real root classification, you get this polynomial of degree 6. So the algebraic boundary, the risky closure of the topological boundary, is an irreducible hypersurface of degree 6. And as always, we make the problem easier by passing to complex projective space. Okay, so I claim the dual cone is spanned by the rational normal curve. So this is the curve parametrically given by 1 x, x squared, x cubed, x to the 4th. And I take the cone spanned by these points. I claim that's the dual cone. Well, let's think about the dual of the dual, right? So what are the linear functionals that are non-negative on this cone? Well, they are the non-linear functionals that are non-negative on this curve. What's a linear functional that's non-negative on this curve? Well, that's a quartic polynomial that's non-negative. Right? So a linear functional that's non-negative on this curve is a quartic polynomial, right, that's non-negative on R. So therefore, that's C dual. This convex cone is a spectrahedron. If you ever meet a convex body or convex cone, the first question you will ask him or her, are you a spectrahedron? Are you a spectrahedron? Right? That's always. If you meet a convex body, the first question is, are you a spectrahedron? This guy is a spectrahedron. It's a Hankel spectrahedron. So this dual body is the set of all, U, blah, blah, and R5, such that the Hankel measure is positive definite. So that is the correct representation of the dual. Maybe one word on sociology. So in pure math, Hankel matrices are called catalecticons. That's a term that goes back to Cayley. In applied math, Hankel matrices are called moment matrices. So if next week at the workshop somebody uses the word moment matrix, so Pablo Parillo, for example, he's an applied person. If somebody says catalecticon, they're commutative algebraists or something like that. Okay? Okay, so Yongnam, the lecture begins now. Okay. So in the next 40 minutes, I'll tell you a tale of 2 cones. Okay? So for simplicity, let's work with homogeneous polynomials. So I'm looking at homogeneous polynomials of even degree 2D in n variables, x1 up to xn. So that's a finite dimensional real vector space. So inside this finite dimensional real vector space, I have a full dimensional closed convex cone consisting of all polynomials that are non-negative. So this is this cone, P and 2D, non-negative polynomials. Okay. Now inside this cone, I have a subcone. There are polynomials that are sums of squares. Right? If you are sum of squares over the real numbers, you're non-negative. So that's some subcone. Draw it like this. So maybe it shares some of the boundary. It goes like this. Okay, that's a subcone. Sigma n 2d. And what I want to discuss is the nature of this inclusion. I want to convince you, I want to discuss, to what extent are they the same and to what extent are they different from an algebraic geometric point of view. Okay? So first of all, are they equal at all? Well, yeah, sometimes they're equal, right? So for example, if d is 1, so if we have quadratic forms in any number of variables, join here or here. You can pull out another chair. So for quadratic forms, they're non-negative by the spectral theorem, right? Because we talked about this yesterday. So quadratic symmetric matrices can diagonalize. So a quadratic form that's non-negative by the spectral theorem is a sum of squares. For binary forms, it's also true. So binary forms are essentially polynomials in one variable, and that's true. So for example, here is a binary quartic, polynomial homogeneous in two variables, and I claim this is non-negative for all values of x1 and x2, and to prove this, we write it like this. Right? So here's a sum of squares representation that proves that this is a non-negative polynomial. Okay? Now the verb write has a little superscript called SDP. Okay? So when I say we write, that means using semi-definite programming, you get this representation fast. Okay? So you take this polynomial, you type it into MATLAB or Sidumi or CVX or whatever SOS tools, and it will produce this representation. Okay? And we practiced yesterday how to do that. Okay? There's one more case. That's the case of plane quartic. So if D is 2 and N is 3, every non-negative ternary quartic can be written as a sum of 3 squares of ternary quartics. Okay? And again, can be written means you can do it using any of the tools, for semi-definite programming. Okay? Now this is an exceptional case, and this exceptional case involves some very beautiful 19th century geometry involving quartic plane curves and their bitangents. There are 28 of those. Now the odd theta characteristics. So there's a lot of beautiful geometry that's behind this theorem. That's the theorem of Hilbert. Okay? That this can be done. And these are all the cases. In all other cases, they're different. You can see my talk is a little old. 126 years ago, Hilbert showed that in all other cases, the blue cone is strictly contained in the red cone. Okay? Now, in this strict containment, there are two smallest cases, right? So the minimal cases. So the first minimal case, if n is 3 and d is 3. So these are ternary sextics, so degree 6 curves in the plane. That's the first minimal case where they're different. And the other minimal case where they're different is n equals 4, d equals 2. So these are quartic surfaces in three-dimensional space. Okay? So what I like to do today, in the next 36, 37 minutes, plus overtime, just like in the game this morning, So in the next 37 minutes, I like to explain the difference between the blue cone and the red cone for those two cases only. Okay? Now in particular, I like to focus now on the algebraic boundary. So the algebraic boundary of the outer cone, so this is the hypersurface that vanishes, the polynomial that vanishes on the boundary. Well, we know what that is. That's the discriminant. Right? In the warm-up, and we saw that the red boundary is an irreducible hypersurface of degree n times 2d minus 1 to the n minus 1. That's the discriminant. Okay? So that's the Out here, polynomials, on the red boundary, polynomials have singularities, and that's given by the discriminant. Okay? Well, this discriminant is also one of the irreducible components in the blue boundary, right? So the red boundary shares some full-dimensional piece with the blue boundary. So therefore, the algebraic boundary of the blue cone contains the algebraic boundary of the red cone. So the blue boundary has several irreducible components, one of which is the red boundary. So we're going to be interested in the other part of the boundary. We're going to be interested in the other part of the boundary. Okay? And as I said, we're only going to focus on these two cases, sextic curves in the plane and quartic surfaces. We're going to work in projective space. So, sextic curves, the ambient projective space has dimension 27. Okay, so this convex body, the slice, is 27 dimensional. Let's draw the convex body, like this, sigma, here's P. And then in the quartic surface case, the ambient convex bodies have dimension 34. So these are the two smallest cases. Let me start with an example of a polynomial that's non-negative, but that's not a sum of squares. That's actually my favorite example. This was published in a little-known paper by Lax and Lax. So this is Peter Lax, who famous PDE, numerical PDE person, Abel Prize winner, and his late wife Annalie Lax. In '78, wrote a paper called On Sums of Squares, where they talk about this example. Okay? So, well, you take 5 variables, and then you go a minus b, a minus c, times a minus d, a minus e, and then symmetric. You add them up symmetrically. Okay? So this is a non-negative polynomial. Well, how can you see that? Well, symmetric, so without loss of generality, you can fix a permutation on a, b, c, d, and e. Right? So you can assume that a is bigger than b, is bigger than c, is bigger than d, is bigger than e. Greater equal. Okay? And then you just look at the signs. You make a little argument, and you see it's non-negative. Okay? Now, likewise, the sum of squares is not so hard to see. So when you analyze this polynomial, you ask the question, for which real values can this be 0? Right? Well, we just had an argument that it's non-negative, so you analyze the cases when it can be 0. And then it turns out that the locus where it can be 0 is too low dimensional. So this can't be a sum of squares. I'm sorry, it's too high dimensional. So it's too big. So the locus, if it were a sum of squares, it would be a sum of squares of quadrics, at least 2 of them intersecting, and that's sort of, a curve, and this curve is too big. Okay? That's the argument. So this is an example of a red point that's not blue. So I think this is a point in P. I think now it's a typo, P42, so P, but not in sigma. So I've given you an example of one point that's over here. Okay? Now why 4? Well, it looks like there are 5 variables, but really there are only 4 variables, right? Because the differences, a minus b, they span a 4-dimensional vector space. Right? So this is really a homogeneous polynomial of degree 4 in 4 variables, or as Luke would say, an element of sim sub 4, C4, dual or not? Okay, anyway, so it's a homogeneous quartic in 4 variables. Okay? So it's a quartic surface. So the question is, what's special about this quartic surface? What makes this interesting? So now I have a pop quiz. So I know in this audience there are some applied people, some pure people, Korea. So do you know what a K3 surface is? So anybody who's heard the term K3 surface, maybe I would like to raise their hands. Have you heard K3 surface? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so about a third of the people. Okay, so the pop quiz, would be what's a K. If this were a lecture in an algebraic geometry seminar, there would be a pop quiz, namely what's a K3 surface. Okay? And we'll come back to that. So I'd like to give you 3 theorems that distinguish the blue cone from the red cone. The first theorem characterizes this blue boundary that's not red. Right? So one way to distinguish them, if I can name this hypersurface, I've given you sort of a description. Right? So it's one way to distinguish them, because on this hypersurface, the lux point is on the other side. Right? So that's sort of the idea. Okay? So what is that hypersurface? So the algebraic boundary of the blue cone in the ternary sextic case has a unique non-discriminant component. So this part of the boundary is given by a single irreducible polynomial. Okay? That's a polynomial in 28 homogeneous variables of degree 83,200. It's a big polynomial. And then there's a description, a parametric description. It's a Zariski closure of sextics that are sums of 3 squares of cubics. That gives a parametric rule. Okay? Then there's a sister theorem, right? So for Cortex surfaces, the algebraic boundary, the blue boundary that's not red, has a unique component, has a unique irreducible polynomial in 35 homogeneous variables of degree 38,475, and it's the closure of quartics that are sums of 4 squares of quadrics. Okay? Now, where do these things come from? Where do these numbers come from? So these hypersurfaces represent something called the Noether-Lefschetz divisor, whatever that is, in a moduli space of K3 surfaces. Okay? So this is some algebraic geometry thing. Okay? But before we get there, so I think, this and this should be understandable to everybody, and this maybe should be incomprehensible to some of you. Now, what's the point of these numbers, right? Why is this interesting, right? Who cares? That's a big polynomial, right? Why does it matter that this has degree 83,200? Well, let me answer that like this. Think about the number 3,264, okay? Eisenbart and Harris writing a book right now that has that title. I think there's a title. The title is, 3,264, An Introduction to Intersection Theory, something like that, right? So this is a very important number. That's the number of conics tangent to 5 given conics in the plane. Okay? And that was found in the 19th century, and there was a lot of development. So first people got it wrong, and then there was a lot of discussion. Eventually people came up with this number, and that was the foundation of the development of intersection theory, a normative algebraic geometry in the 20th century. And, as I would say, the development of numerical algebraic geometry in the 21st century. Okay? So a very important number. So understanding these numbers is not so much that the number is important, it's the insight. You learn the structure, the mathematical structure that's behind these numbers. That's why these numbers are important.
I should say 3264 is also important for real algebraic geometry.
Because you can realize them all real? Or?
Yeah, it's a fault to realize them.
Okay. Anyway, so that's the number. So this paper appeared in the meantime. So our numbers are coefficients of certain modular forms in a paper by Molik and Pandarapanda. And the title of that paper is Gromov-Witten theory and Noether-Lefschetz theory. Okay? So I'll tell you more about these things as the talk goes on. But okay, so that was my first theorem. The first theorem tells you what's the blue boundary that's not red. Now comes the second theorem. The second theorem concerns the red boundary that's not blue. Okay? So suppose you optimize a linear functional over this convex body, what are the red points at which the optimal value can be attained? That's not blue. Which red points can be the solutions to a linear program on this body? What are the extreme points that are red but not blue? Okay. And that theorem describes that. So extreme non-negative polynomials. Now the extreme part is a lower dimensional variety. If you have a convex body, such that this coffee cup, right, the boundary is a 2-dimensional set. But the extreme points is a 1-dimensional variety. Right? So by an extreme point, I mean one at which a linear functional can uniquely attain its minimum. Right? So there's a 1-dimensional variety of extreme points in the 2-dimensional boundary of this 3-dimensional convex body, which happens to be a spectrum. Okay? So in this body, we have a what do we have? We have a 27-dimensional convex body with a 26-dimensional boundary, but the extreme points have codimension 10. I'll tell you what they are. Okay, so we take the set of extreme rays in the cone. So these are extreme rays in the red cone that are not blue. And we take the Zariski closure. We get a certain variety of codimension 10. So it's a projective variety of dimension 17 in the P27 of all sextics. And we know the degree. The degree is 27,312,976. Okay? Why do we know this degree? Well, that's the Severi variety of rational sextic curves in the plane. That's a Gromov-Witten number. Right? Many people know this number. Right? So pick 10 points in the plane. How many rational sextics pass through 10 given general points in the plane? Okay? So at the KAIST algebraic geometry, DCC, Dijon meeting in August, if you say 26,312,976, half of the participants will know this Gromov-Witten number. Okay? I'm joking, of course, a little bit, but it's a very well understood situation. This and its generalization has been studied by many people. Okay? So that's the Severi. Now the analog for Cortex surfaces is unknown. It's an open problem. Okay? So, well, we still have a description, still codimension 10. So we look at the set of extreme rays of, again, that is blue but not red. That variety has codimension 10 in a 34-dimensional coffee cup, 34-dimensional convex body. It's the variety of quartic symmetroids in P3. So these are quartic surfaces that have a symmetric determinantal representation. That's a defining polynomial is a determinant of a complex symmetric 4x4 matrix of linear forms. It again has codimension 10. It's a 24-dimensional variety in the space of all quartic surfaces, and that variety is hard to study. So I talked to experts, including Pandre Panda, and they believe that a significant advance beyond, Gromov-Witten theory on surfaces will be needed to get a handle on this object. Okay? That was my second theorem. So the second theorem tells you what are the extreme red points that are not blue. Is that clear? Please interrupt me. Okay? So I throw in, algebraic geometry jargon, so to keep Professor Lee happy. But other than the basic statements about red and blue, everybody should understand. Rainer.
What's the Zariski closure of the blue extreme rays?
I don't know.
Lose something? Is it clear that the very variety, for example, doesn't include the extreme rays of the SOS?
That's a great question. I don't know the answer. So the question, so probably not. Probably there are more extreme rays out here. Yeah, I don't know the answer. Great question. You figure it out this fall with Greg, okay? Okay, so that's the second, theorem. So let me give you the third theorem. Okay? Yes, Luke.
Do you try numerical experiments for finding a number?
We'll get to that. Yeah, no. So this we cannot get by numerical algebraic geometry. Well, I'll get to numerical algebraic geometry. So no. Okay? So I don't know this number, and I think it's out of reach right now of numerical algebraic geometry.
26 million.
But
Even 26 million.
exactly, these are too big. Those numbers are too big at the moment. Okay, here's my third theorem. Okay, now the third theorem goes back to the characterization of the blue thing, but it's the dual characterization. So let me explain this. Okay, so I'll draw a second picture. So here is my inclusion. Let me draw the dual inclusion. Well, if I have the dual body, so here I have, sigma dual, or maybe I called it check here, I forgot the notation, the dual convex body, and then, this contains the dual of P. Right? So, if you have two closed convex cones in a finite dimensional real vector space, then one is strictly contained in the other if and only if the same happens on the dual. So if I want to convince you that blue sigma is strictly contained in red P, I might as well convince you that red P dual, a red P dual is strictly contained in sigma dual, blue sigma dual. Right? I'm going to do that. Now I'm going to find, the extreme rays not on sigma, but on sigma dual. So now I'm going to turn the blue convex body in the coffee cup, and I tell you what are the extreme rays, the dual blue but not dual red. Or equivalently, we're going to tell you what are the hyperplanes that are tangent at a blue point that's not red. Okay, so a hyperplane that touches at such a point will be dual to an extreme point over there. Yeah. Right, because it's supported by hyperplane, and then that's the point. Right? So I'm going to give you, in algebraic geometry language, the dual variety of the earlier hypersurface. And here it is. Okay? So I formed this Hankel matrix. This is a 10 by 10 Hankel matrix. Catalecticant for pure mathematician. Moment matrix for applied mathematician. Generalized Hankel matrix for Rainer on Monday. So this is a 10 by 10, Hankel matrix. And the entries are the coefficients of my ternary sextic. My 28 coefficients of my degree 6 homogeneous polynomial in 3 variables are in this matrix. Okay? Let's look at 10 by 10 matrices like this. This is sort of my favorite spectrahedron from the first hour, right, essentially. So I take matrices like this of rank at most 7. Okay? So we're looking at the Hankel rank. So this afternoon, Dr. Wu will talk about symmetric tensor decomposition, and there's a Hankel rank and cactus rank, and that's one of them. Okay? So I look at Hankel matrices of rank at most 7. So that, I claim, is a rational projective variety of dimension 21, codimension 6, and degree, small degree, 2640. And it's the projective dual. It's a dual hypersurface to the Zariski closure of sums of 3 squares of cubics. So it's the dual of this hypersurface. Right? So this hypersurface is dual to the codimension 6 variety of dual blue points, dual extreme blue points that are not red. That's the thing. I'm actually going to prove this theorem. I'm going to give you a proof. It's a statement clear. Right? So I claim that if you have a point out here, a linear functional, you write out the 28 coefficients, then the Hankel rank is at most 7. And you already see, how this might have to do with the description down there. Okay? I'm going to prove this. Okay? Well, how can you show that a variety is rational? Well, you want to show it's birational to some other variety that's rational, and the variety we're going to use is the Grassmannian. Okay? So let's look at a Grassmannian of 3-dimensional linear subspaces in a 10-dimensional space. Okay? So this is a rational variety of dimension 21. Okay? That's 10 minus 3 times 3. 21-dimensional variety. Okay? Now the ambient space, the ambient 10-dimensional space is ternary cubics. So take the space of ternary cubics and I look at 3-dimensional linear subspaces. Rational dimension 21. Okay? So now I'm going to do the following. I'm going to take a map from this Grassmannian into some projective space of dimension 27, and it's the projective space on this side of the blackboard. It's the dual to the projective space on this side of the blackboard. That is to say, I take the space of ternary sextics, the dual linear functionals on that, and I take the corresponding projective space. That's this projective space. Okay? And so I'm mapping this Grassmannian into this projective space by a map called the global residue. Okay? So how does that work? Well, if I'm in the Grassmannian, I have a 3-dimensional, that's specifying 3 ternary cubics. Right? So a point here is represented by 3 ternary cubics. Let me assume that these three cubics in the plane don't meet. They don't have a common point. The resultant is non-zero. Well, then, outside this resultant, there is a map called the global residue. So it's defined whenever my ideal is a complete intersection. Here's how it goes. So the value of this map. So I'm mapping into this dual space. So the image is a linear functional that eats ternary sextics. Okay? So Frank gives me three cubic curves in the plane. I have to make a linear functional that eats your sextics and makes a number. Okay, so Frank gives me three cubics. You give me a sextic and we make a number. Okay, so here's how we do it. Okay, so it is the image of P mod the ideal of F. That's the abstract rule. Well, this ideal is Gorenstein. And 6 is the Sokal degree, right? So Frank gives me three cubics. That three cubics defines a Gorenstein ring. In degree 6, there's the Sokal as a one-dimensional vector space. So your sextic, you know, it lives mod Frank's ideal in a one-dimensional space. So it's a number. That's clear? So he gives me ideal, you give me a ternary sextic. That's a number, right? How do we find that number? By the division algorithm, right? So we take the Gröbner basis normal form, right? So I take Frank's cubics, I calculate the Gröbner base in any term order, I take your sextic, I take the normal form, I get a number against the unique standard monomial in that degree. So I've given you the map, okay? So now, so I claim that this map from Frank's cubics to my linear function is birational. It has an explicit inverse, right? So I take my L, I write it as a Hankel matrix, and I take the kernel. And that kernel is a three-dimensional space. So I can go back, I can recover Frank's cubics as the kernel of this matrix. Right? So the linear functional, I evaluate it, 28 times, and I fill this matrix. It's going to be a rank 7 matrix, has a three-dimensional kernel, and that's it. So that's why it's birational. So the inverse simply maps the rank Hankel matrix to its kernel. The degree formula, well, minors or Cohn-Macaulay, so it's a standard formula for the degree. Okay? So that's it. That was the only proof in this lab. It wasn't so bad. It was supposed to be intimidating, but didn't succeed. So there's a cousin theorem, it's the same thing for quartic surfaces. So you again have a 10 by 10 Hankel matrix that you now fill with the 35 coefficients, duals, of ternary quartics, and a similar theorem. So now we take the 7 by 7 minors. So the above Hankel matrices of rank at most 6 define a rational projective variety of dimension 24 and this degree, 28, 3, 14. And the dual is exactly what we have. Okay? So I'm done with my three theorems. I've given you three theorems that convince you that the blue cone is strictly contained in the red cone. First theorem, I described the blue boundary that's not red. The second theorem, I told you the red extreme points that are not blue. And then in the last theorem, I did this dually blue dual extreme points that are not red. Let me come back to the first theorem. Can we trust Maulik and Panduripanda? Well, that's a crazy question, right? These are very distinguished algebraic geometers, and we should trust them, right? We have every reason to believe that they know what they're doing. They're wonderful people, so we should trust them. Nevertheless, it never hurts to check. Okay.
Well, they
so what?
Mistake when they program Maple.
So what happened? Okay. So what happened is everything in their paper was correct, but their paper dealt in a very, very abstract setting. So they computed something in a very abstract setting, to be explained shortly. And we took a result from this very abstract setting to a very, very concrete setting, right? Coffee cups in a 34-dimensional space, very concrete. And along the translation, there were a couple steps that were not so clear. And we were off by a factor of 2, twice in opposite directions. And there were many emails, between Ranestad and Panduripanda. So Tauenstein came on the board and he independently verified these numbers. And that really, really was extremely useful for the project And in the end, the theoretical proof worked out okay too. Okay, so it never hurts to double check. Okay, so they were independently verified using Bertini. It's an amazing piece of software, for algebraic geometry. There are many authors. Matt is on the team. He's here. And even if you don't attend next week's NIMS workshop because you have to go to a different summer school, while at that other summer school, you can still try Bertini on your problems. So I recommend it. Okay? So we computed these degrees for the irreducible values of interest by intersecting a generic linear space of complementary dimension. Okay? And Bertini does this numerically. And if that degree is in the order of 30,000 and you have John Hauenstein as a co-author, you can do it. Okay? And if, it's a little smaller and you have Luke, so people live different levels of expertise. So I can do tiny examples, and Jose can do bigger examples, and Luke can do a little bit bigger, and then Hauenstein can do even bigger. But we can't do 26 million, and we can do 80,000. Okay? So that's roughly the situation. Okay? Okay, so now I explained 3 theorems. And the first theorem with these degrees, there are 2 proofs. There's a numerical calculation and then there's a theoretical proof. So I'd like to tell you a little bit about the theoretical proof. And I will end in time. Pop quiz. What's a K3 surface? Well, for the students, suppose you don't know, right? Young people go to the wiki, the source of all wisdom, right? So according to the wiki, K3 stands for 3 mathematicians, Komor, Kela, and Kodaira. Further, the wiki tells us that K3 surfaces are complete, smooth surfaces that have a trivial canonical bundle and are not abelian surfaces. Okay? So that's a definition of a K3 surface. Now, they don't have to be algebraic, actually. They can be analytic. Same definition works. But here we're going to be interested in algebraic K3 surfaces. Okay? Now that's a nice definition, but it's not so enlightening, from an applied computational point of view. Because how would you meet a K3? How would Feng meet a K3 surface? So I'll tell you. Okay. So the way you would meet a K3 surface is in 2 ways. You could meet them whenever you meet a smooth quartic surface. A smooth quartic surface in 3 space is a K3 surface. The other way you could meet a K3 surface is you have a sextic curve in the plane. Right? If you have a degree 6, let's say smooth. Suppose you have a degree 6 curve in the plane, and you have a surface that maps in a 2-to-1 way onto the plane, that double covers the plane, and the branching is along the sextic curve. Then you have a K3 surface. Okay? So these are 2 natural families of K3 surfaces that you might run into. Okay? That in fact Hilbert ran into. Right? These are exactly the 2 Hilbert cases. Right? The 2 smallest cases where sums of squares differs, where blue differs from red, are exactly these 2 cases. Sextic curves in the plane, quartic surfaces. Okay. So those are the standard models. Now, there are many other. So the algebraic families, they come in, there's a countable union of moduli spaces. So this is sort of level 2. Level 4, there's level 6, level 8, so there are many other families, but these are the 2 lowest levels. Okay? And these are our families. So up to isomorphism, these are 19-dimensional families. So here's a theorem. There's a Noether-Lefschetz theorem. And the short modern version says that general K3 surfaces in these and other families have Picard rank 1. The Picard group is Z. Okay? The Picard group is the thing that you study when you get into chapter 2 of Hartshorne, when it gets hard. Okay? So for students, so it's a character building experience. So to prove your manhood or womanhood, you're supposed to study Hartshorne's book. And it gets hard when you get into chapter 2, when you learn about the divisor group and the class group and all that kind of thing. Weil divisors and Cartier divisors, and that's how you prove your womanhood or your manhood, okay? By studying that stuff.
And then you switch to PDEs.
And then, pardon me?
And then you switch to PDEs.
And then you switch to PDEs, exactly. Anyway, in English, okay? Let me translate that, what this means in English. So there was an older version that was proved by Max Noether in 1882. That's the dad of Emmy Noether. Okay? So the dad proved the following theorem. every irreducible curve on a general quartic surface is the intersection of that surface with another surface. Okay? That theorem is a big deal. Okay, let me tell you why that's a big deal. Okay, suppose you have a surface in 3 space. Okay? How could you make a curve? Abraham, how can you make a curve on a surface? Well, you could intersect the surface with another surface. That gives you a curve. Right? But in general, there are many more curves on the surface. Right? Think about the cubic surface. The cubic surface has 27 straight lines. Right? And the plaster models, right? You go to any Italian or German math department, Felix Klein had them made, you can look at them. Okay? So those you don't get by intersecting the surface with another surface. You just don't. So typically, it's not the case that every curve on a surface comes by intersecting with another surface. But for a very, very, very general quartic surface, that is the case. So that's Noether's theorem. Okay? So that's behind this. Now, by a Noether-Lefschetz divisor, we mean a family of surfaces where this fails. Right? So Noether-Lefschetz divisor is, you're in such a divisor, that means you are, for example, a quartic surface that has more curves, that has some curves on it that you cannot get by intersecting with another surface. So how is this related to our discussion? Well, in our discussion, for example, we were talking in the quartic surface case, we were talking about quartic surfaces quartics that are sums of 4 squares of quadrics. Okay? So for example, so the exceptional, so the blue boundary that wasn't red, right? So they look like this. A squared plus b squared plus c squared plus d squared, where a, b, c, and d are quadrics. Okay, now we can do the following trick over the complex numbers. Okay, so keep me honest. Young-Suk, you help me out. He can check these identities. So a plus ib, a minus ib minus c plus id minus c minus id. Okay, so this determinant, right, is a quadrix. Right? So my representation over the complex numbers is the same as this representation. So if you have a quartic surface that's a 2 by 2 determinant of quadrics, that's exactly the blue boundary that's not red. Right? But let's think about this. So how can this determinant be 0? These are quadrics. Quadric, 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 quadric. Right? Well, one way this could be 0 is the first row is 0. Right? That makes the determinant 0. So then you have the intersection of a quadric surface and a quadric surface. Okay? That's an elliptic curve. Okay? Now, for the students, here's the problem. Right? So you study chapter 2, and then many give up and do PD, and some make it, through sheaf cohomology and so on. But you never make it to curves and surfaces, right? So you never learn that if you intersect a soccer ball and an American football, you get an elliptic curve in the boundary. Okay? So this is an elliptic curve. A quadric intersected another quadric is an elliptic curve. And there are 2 families of elliptic curves. One coming from the row of this matrix, and that says the Picard rank is 2. Okay? So these elliptic curves, you don't get by intersecting the surface with another surface. Now the other one, if you take P2 times P1, also known as the Toblerone in toric circles, right? So you take the Swiss chocolate, known as Toblerone, then you multiply the triangle by a factor of 3 and the edge by a factor of 2. Okay, you get something called a reflexive polytope. It has 1 interior lattice point. Again, take the Swiss chocolate, multiply the triangle by a factor of 3, and this direction by getting 1 interior lattice point. So this means, the hyperplane section is a K3 surface. So a K3 surface is also known as Calabi-Yau two-folds, if that helps. Okay, and then there's a map. There's a map to this P2 and that P2, and again that makes two curve. The fibers are families of gives you 2 families of curves that are not that independent. Okay, that's the end of my talk. So that's behind all of that. So that's the last slide, and I apologize for the overtime. Hope there weren't too many penalties and red cards. So right now, thanks to optimization theory, lots and lots of exciting advances in optimization have led to renewed interest in a topic that's over 100 years old, namely the inclusion of the blue cone of sums of squares inside the red cone of non-negative polynomials. Questions that we might ask are, for example, what is the Zariski closure of the extreme rays of the big cone that are not in the small one? Okay? What is, the algebraic boundary that's blue but not red? And what are the duals of these varieties? What can we say about the duals? In this talk, we touched the tip of the iceberg. Right? We only looked at the two smallest cases where blue and red differs, right? Namely the case of ternary sextics and quartic surfaces in 3-space. But we already discovered in these two very simple cases that there is a rich and interesting connection to topics in algebraic geometry, right? So, for example, here we were led to Gromov-Witten theory. We saw the Severi variety and the more mysterious variety of symmetroids. We talked about the Noether-Lefschetz divisor, so Noether's theorem on the previous slide, and we talked about non-trivial issues having to do with ranks of Hankel matrices, which again we'll learn more about this afternoon in Dr. Wu's talk. So these are the beginning. These things get very, very interesting for larger values of n and d. Greg Bleckerman and making very, very good progress. He has some help from wonderful postdocs next year. But there's a lot of interesting topics. Mauricio Velasco published a paper with the co-authors where he generalized this to toric surfaces, a beautiful, beautiful theorem that ties in and that he will report in a 1-hour talk on Thursday. So I know that some are coming back from the summer school and listen on Thursday afternoon, but even if you can't make it, we're all here, for another 2 months and happy to talk. Thanks for your attention.